Hello everybody, we're going to do discontinuous functions today and emphasize on the different types of discontinuity. So as we all know that for a function to be continuous, the condition is that the left hand limit is supposed to be equal to the right hand limit is equal to the function at that point p towards which x tends to move closer, that is towards which we are finding the limit. So if any of these conditions isn't met, the function is said to be discontinuous. Let's take a first case, that is the limit doesn't exist at that point p, that is the LHL is not equal to the RHL. And the second case is that the limit exists at that point p but is not equal to the function's value at that point p. These are the two main types of discontinuity. There's a third type of discontinuity as well, which we'll discuss towards the end of the class. So let's take a function to discuss these two types of discontinuity. Let f of x be defined as x plus 1 for x between -2 and 0. It is an open interval, and a function is 2 for x equal to 0, and for values of x between 0 and 2, function is -x, and for x equal to 2, function value is 0, and for x between the values 2 and 4, x minus 4. Let's plot the graph of this function to actually make it evident that at certain points, certain values of x, the function is discontinuous. Okay, our first function between -2 and 0 is x plus 1. Let's plot the graph for x plus 1. At x equal to -2, we have -1 value, and at x equal to 0, we have 1. But you should notice that the function is not defined for -2 and 0 when it is equal to x plus 1. So we represent it with these undarkened circles. It passes through -1, it's a straight line. Now when x is equal to 0, the value of y, that is f of x, is 2. Since it's defined as a point, it's a darkened circle. Now for 0 to 2, that is 0 to 2, this particular range of domain of values, it is f of x is -x. As you all know, it is not defined for 2 and 0 over here. And at x equal to 2, that is over here, the value of y is 0, and at x between 2 and 4, x is lesser than or equal to 4 over here, so hence the function is defined at 4 but not at 2. X minus 4, the graph will be as follows. As you can see, that it is evident from the graph that the function is not defined at the point -2 and is discontinuous at the points 2 and 0. That is, f of x is not defined at -2 and at x equal to 0 and at x equal to 2 there are points of discontinuity. Now the types of discontinuity over here is different, and I will prove and explain the different types of discontinuity by using the concept of limits again. This graph is no longer needed. At x equals 0, we know that the function is 2. Now let's check the left hand limit of the function. That is limit x tends to 0 from the negative side, that means from the left hand side of f of x. As you all know that as we approach the value of 0, for which x is less, in this case the function is x plus 1. Hence if I solve the limit over here, it is equal to 1. Therefore LHL is equal to 1. Now let's see whether the RHL is equal to 1 or not. For RHL it is limit x tends to 0 from the positive f of x. When I approach 0 from the right hand side, the function is minus x. And so if I apply the limits, the value I get is 0. Clearly RHL is not equal to LHL. So the question of a continuous function is ruled out, and this type of discontinuity is called a jump discontinuity. As you must have noticed in the graph that I had drawn previously, that when I approach towards z0 from the left hand side, it moves closer and closer to the value, but suddenly jumps to a value of 2 when x is equal to 0. But when I approach the limit of the function from the right hand side of 0, it goes according to the function of minus x and does not reach 2 as well. So there's a certain sudden jump in the value towards 2 when I approach from the left and the right hand side, and hence when the limit does not exist at a point, I can name that type of discontinuity as jump discontinuity. And the limit does not exist. Now, the other point of discontinuity was x equal to 2. Let's check the limits at x equal to 2. Left hand limit is for the function minus x is minus 2. Now let's see whether the right hand limit at the point 2 is minus 2 or not. The function when we approach the point 2 from the right hand side is x minus 4, and hence it is also equal to minus 2. Over here you can see that the left hand limit is equal to the right hand limit, but for a function to be continuous at the point 2, we also need to satisfy that the limit should be equal to the value of the function at the point 2. Now, this type of discontinuity in particular is an interesting one because the function at the point 2 is 0, but we are able to remove this discontinuity if we redefine the function at the point 2. So if I redefine the function at the point x equal to 2 as minus 2, then I will be able to remove that discontinuity and satisfy the condition that LHL equal to RHL is equal to the function at the point 2, and hence it's continuous. So this type of a discontinuity is called a removable discontinuity. Now, the third type of discontinuity happens when at a particular point of x, that is when x tends to move closer and closer towards some value p, the value of f of x tends to move towards infinity. It is a common example. We'll take another function. If I draw the graph for this function, you can see that as x tends to move closer to 0, the value of y moves closer and moves away, and hence it is going towards infinity. So if I have the limit of x tends to 0 for f of x, it is equal to infinity, and this is also shown separately in terms of its right hand and left hand limits. Over here, if I tend to move towards 0 from the positive side, that's from the right hand side, not exactly the positive side, from the right hand side, the limit of the function is plus infinity. But if I move, this is under RHL. But if I move the value of x towards 0 from the left hand side, the value is minus infinity, as you can see. Hence, the limit itself doesn't exist, and this function is said to be discontinuous. And this type of discontinuity is not even removable. And it's also called infinite discontinuity. Now, over here, when x tends to move towards a particular value, p, we see that the function f of x tends to move towards infinity. Plus or minus infinity doesn't matter over here. Now, this value of x turns out to be a vertical asymptote for the function. What is an asymptote? Let's take an example of a function. Over here, if I have a particular value of x which tends to p, this value p would turn out to be a vertical asymptote for this function. Similarly, if I have a value of function f of x for which x tends to infinity, then this turns out to be the horizontal asymptote for that function. So if I draw the graph of this function, it will be evident from the graph of this function that at x equal to 3 we have a vertical asymptote and at y equal to 2 we have a horizontal asymptote. Okay, now let's check whether that condition for when x tends to p, f of x tends to infinity, is satisfied for this particular example. Over here it is evident that x equal to 3 is the vertical asymptote. So when limit of x tends to 3, let's see what happens to this function. Obviously when I substitute the value x tends to 3 over here, we get 0 in the denominator and this will be equal to infinity, and as this is satisfied, so x equal to 3 is a vertical asymptote. And for the value y equal to 2, so I need the function over here to be 2. I need a particular value over here, x will tend to infinity. So at which point of x tends to, if x tends to infinity at the value y equal to 2, that will turn out to be a horizontal asymptote. Let's see whether at x tends to infinity we get the value y equal to 2. I'm dividing the numerator and the denominator by x. Now if I substitute the limits, this and this will become 0, so I'll be getting 2, and hence f of x equal to 2 is a horizontal asymptote. This is the main concept behind infinite discontinuity, and hence this is an example for infinite discontinuity. Thank you.